everyone. So, this week we will be looking on entropy. I hope I am audible to everyone. Let me check my recordings. All right. So, this week we will be dealing with entropy. For the people who joined for the first time, I am Ganesh Kumar. I am PhD students at IIT Gandhinagar. So, my research work involves uh, developing a computational framework for a novel solid rocket propellants for combustion and propulsion of solid rocket propellants. So, my research work involves combustion, multi-phase modeling, CFD, and rocket propulsion. So, it's a combination of all these, and I will be the tutor for this course for for this. I mean, I will be conducting the interactive sessions. Uh, so this is supposed to be interactive. You can feel free to switch on your mics and camera, and you can stop me anytime, and you can ask me questions. And uh, so, if you have any questions regarding the course contents taught till now, and whatever we discussed last week, if you have any questions, you can ask me now. If not, we will go forward with the today's questions.
Good evening, sir.
Yes, Amir. Good evening.
Sir, I have a question regarding lecture one of week two, where
Okay.
we discussed about an irreversible process which can be replaced by a reversible one, provided we are dealing with the same initial and final state.
Correct.
So this is clear that if the initial and final states are same, so whatever the state function will be won't change irrespective of the process followed. But what about the energy interactions? They definitely won't be the same, as reversible processes are more efficient ones. So how can we allow, as it was written, that this interchange is allowed? So how can we do this if energy is definitely going to be different, energy transfer?
Right. So, if you look at the entropy, this is just to find entropy between during the process. Since entropy is a
Okay.
state function, you can
Yeah.
replace that irreversible path with a reversible path, and you can come up with you can find the entropy change in the process. Only for entropy we deal with this. To find the energy transfer, you cannot do that.
Yeah. Okay. So, sir, maybe the idea is that we want to know that for a very perfect system, the entropy change, which would be because of the reversible heat transfer, would be this much. So, this will give us an idealization, I guess, in that case.
Yeah, that is true. The um, important thing is entropy is a state function, so
Yeah.
it doesn't depend on the process. Either if you go reversible or irreversible, it doesn't depend on the process. It just depends on the initial and final state, provided the initial and final state should be in equilibrium, right? Uh,
Okay, sir.
and entropy is also defined. If you remember, entropy is also defined for reversible heat,
Yeah.
right? So
Yes, sir. For
that
process
is one
state.
of the reason that we can, since entropy is also state function and it is also defined for reversible heat, we can do this technique to find entropy.
Okay, sir. That is clear. Thank you.
All right. Uh, does anyone have any more questions? No more questions. Today, what we will do is we will solve few questions. As usual, we will solve 5 questions. If possible, we'll try to complete all five. If not, you may need to complete it by yourself. Uh, The agenda is we have 5 questions. We can complete it today, and it is based on your week 2 content. And keeping in mind the assignments you will be facing, assignments, keeping in mind the assignment 2. I made these questions based on that, based on the questions which I see in assignment 2. So um, let's get started. We have This is our first question. It's an easy question. What we are going to do in all these 5 questions is to find entropy and try to understand its implications on physical system. Like, why do we need to find entropy? If we find entropy, uh, what we know about that system. So that is how all these questions are made. Okay. So the first question is, air in a piston cylinder assembly undergoes a process from state 1 to state 2. So state 1 is characterized by these two state variables P1 and T1, whereas state 2 is T2 and P2. It's given. Using an ideal gas model for air, determine the change in specific entropy between these states. Okay, this is without internal irreversibilities or with internal irreversibilities. What is the change in a specific entropy? Is that it's what been asked. So let's try to draw a piston cylinder assembly. So you can consider this as your cylinder. This will be your piston. It's a closed system, and you can write state 1 is state 2. T1 is 400 Kelvin and P1 is 200 kilopascals, and state 2 T2 is 600 Kelvin and P2 is 750 kilopascals. So we need to find change in entropy. How do we find it? Change in specific entropy. We can put something like this: delta S or ds. You can write delta S. It's an ideal gas. Important thing to note.
So CPLN T2 by T1 minus.
Okay.
Can you use
Cp
that ln T2 by T1 minus T2
T2.
by T1? T2 is ln RLN P2 by P1.
Okay. This is delta S, right?
Yes, sir.
Do you know how do we get this equation? Basically, it arises from ds is equal to, or generally TDS is equal to du. How do we write? dH minus VdP, right? It's basically coming from combining first law of thermodynamics and second law of thermodynamics. So basically, first law of thermodynamics tells du is equal to del q, or it's an exact differential, uh, and del. So del, as we know, work is nothing but PdV, and um so this can be written as du is equal to del q minus PdV, and then what we also know is ds. Ds is nothing but dq by, or del q in this case, by t. So when we use these two equations, in addition, h is equal to U plus PV, I believe, right? So use all these three equations together, we will end up with this equation, and this equation is responsible for this expression. Okay, you can even write it in terms of U, which will leads to V2 by V1. Okay. Okay. So, oh, all right. So, what is CP?
CP4 here is 1 kilojoule per kg.
Take 1 kilojoules per kg Kelvin. Okay.
Yes, kg Kelvin.
So, if we do it, what do we get? E2 is 600 Kelvin divided by 400 Kelvin. R. What is R? It's 287, right? So, if you put that also, 287 into ln of P2, 750 kilopascal by 200 kilopascal. 750 by 200. Are you getting? You need to understand one more thing. While developing this relation, we made an assumption. Can you guys guess what assumptions we made while developing this equation? After substituting all these things, we made one assumption.
Uh, Sir, first of all, when we write the first law, we have written work as PdV. So that is for a quasi-static process. And also, the general first law also includes kinetic and potential energy changes. But if we consider a simple compressible stationary system, in that case, we write it this way. So that is the first assumption that I can see. Other than that, sir, ds is exactly equal to del q by t for an internally reversible process. So I think these two are definitely there.
Wonderful. Uh, but after doing this assumption, there is one more assumption pending. You missed one more assumption. After how when we get this relation.
Sir, CP is taken constant, I guess.
Wonderful. So here we made CP to be constant. So CP is not a constant
Yes, sir.
because it's a function of temperature. Here we made CP to be constant. When we made CP is equal to 1 kilojoules, it's a constant. So yeah, please keep that in mind. And if you want to be more accurate, then you may need to use you may need to use CP as a function of temperature. Maybe
Yes,
you
sir.
can use a there is a Janov polynomials is available. Maybe you can use that polynomial which is a function of temperature, and then you may need to integrate and get the entropy. So for now, for this question, if CP is given, just we can use CP.
So can you say once again say that first assumption, other than the CP is constant?
So there are a few assumptions. Uh, First is it's a pure and simple incompressible simple compressible substance, which means there is only PDV work to the substance. Okay, there is no other work. So that's why we were able to write like this. Okay, and it is an reversible process. Is that yeah? So we take it to be reversible. That's why we were able to write this also, and then we were CP is to be constant, and we were able to end up getting this. Is that what Hamid you told?
Yes, sir.
Yeah,
Definitely.
yeah.
And there is a quasi-static work as well. So
Right,
PdV.
right. Quasi-static. So basically, in thermodynamics, we don't deal with study in equilibrium states from one state to next state how it is happening. So everything we always assume, most of the thing we'll assume quasi-static. So is
So
that
for
clear,
the
Francis?
CP, for the CP, you said that there is an equation. Can you say once again
Right.
what's
So there are you can either use equations or you can use tables. Okay. So there are equations called Janov polynomials. Um, So these we typically use it in combustion. In most of the cases in combustions and yeah, mostly in combustion science we encounter CP, and CP is an important property. So we have to be more accurate. We cannot take a constant CP. So at that time we use polynomial. It's actually an eighth order eighth. Um, it's a kind of different polynomial. If you look at it, it will be a1 plus a1t a2t, where I think it goes up to t power 5 or 6. Okay. So this is you can search in internet, or you can even get it in NIST data. Okay.
so if the CP and CV there is a name, if there isn't a name calorimetric or there is a name for if gas is constant CP.
Can you repeat, Francis? I didn't
So
get it.
is there any name for the gases which CP is taken as constant? I mean calorically perfect gas or something. Calorically perfect gas or
So um, okay. See, calorifically perfect gas is where we have dH equal to CpdT, right? So that equation is called calorifically perfect gas equation of state.
okay.
So it has nothing to do with Cp. Cp is always a function of temperature. We cannot take Cp to be constant. So calorifically perfect gas equation of state is nothing but dH equal to Cp dt. Um, yeah. So and this is one of the equation of state. Like we have ideal gas equation of state. PV is equal to nRT, right? Similarly, to relate enthalpies and temperature, we have dH equal to Cp dt. That is the calorifical equation of state. And uh, we normally do not have Cp. We always have Cp as a function of temperature. Yeah. So there is, in
Uh,
reality, it's not a there. Amit,
Sir, the relationship, yes, sir. Sir, is it a partial derivative or a total derivative, this dH?
which one you are talking about?
Sir, dH is equal to CpdT can be written for ideal gas when Cp is very
Derivative. It's a total derivative.
yeah. But sir, real gas does have Cp varying, I guess, with respect to temperature and pressure. Is there a, because we normally write it as a partial differential.
Correct, correct. Right. So here it is total derivative. The you are referring to this equation, right?
Yes, sir, that is.
CPDT. This assumption is called calorifically perfect gas assumption. In
Yes.
real, it no need to follow this. And CP is also, as you said, can be a function of other variables also. This is called calorifical, or you can also take, you can also say it's a calorific equation of state. In real gas, there can be a different calorific equation of state.
Sir, I would like to add one thing, sir. In chapter 4 of Sengel, figure 424 has given a graphical representation of gases, various gases, where we have taken Cp as function of temperature, and there the monoatomic gases,
Mm-hmm.
argon, neon are taken as constant, and the triatomic gases has the most, very steep variation with respect to temperature. But for air and also for nitrogen and air, so the variation is very gradual. That is why we take normally as constant for air or other kind of a gas. CP.
Yeah, yeah. But if you go into and you will know about it. In for air
Yes.
also you will first of all, air you won't consider it as an air. You will consider it as an O2, N2, argon, and mixture of all the other species. At that time, O2, N2, everything has its own functions actually.
Okay.
Uh, whatever you said is true. Sometimes when the it also depends on temperature difference. So we have a temperature difference of 400 to 600 Kelvin. It's a small temperature difference. We no need to use CP as a function of temperature, right? So
Okay.
there will not be any big difference. I will look into that graph. Said where was it?
Sir, it's Angel, chapter 4. It's figure 424. Yes, sir. It has also mentioned the relations, but I don't know if they are Jain polynomials. They
Okay,
definitely are
yeah,
polynomials
yeah,
of some
yeah.
polynomial.
Usually we use polynomials. There are different polynomials. They for different temperature ranges also we have different polynomials. Yeah.
Okay, sir.
So what was the entropy? Coming back to our problem.
So I think it's 26.1.
Okay, thank
Both
you.
are clear.
26.1 is it? Is everyone getting same value?
Yes, sir, 26.12.
Kilojoules per kg kg. By the way, so we have one more thing. If the process occurs without internal irreversibilities and with internal irreversibilities. So what is this change in entropy? Without internal irreversibility or with internal irreversibility?
So it's without any errors.
Why is it without internal irreversibility?
Actually, it is greater than 0 slip. So for the reversible, it will be greater than 0 slip.
Yeah, if we have internal irreversibility, how do we find it?
We need to find that delta is generated. Delta is generated with the reversible.
Delta S.
Delta is reversible equal to delta is reversible plus delta generated.
Is that what you're telling?
Yes, sir.
Any thoughts?
Sir, I guess the S generation will be an exact inexact differential, so it should be a del.
Inexact differential. Is it like this?
Yeah, yes, sir.
How do we find ds generation?
So, but the entropy is a property, isn't it? So, all the properties will be exact, isn't it?
Okay. So you are telling for both with internal irreversibility or without internal irreversibility, we will have same entropy, same change in entropy.
No, what I'm saying is, can we write that is entropy as a inexact equation. I mean, the entropy is a property, so it should be exact equation, isn't it?
Okay, it should be exact. You are telling ds everywhere. All right. So any other thoughts?
Sir, sometimes we compare the values. So whatever we like, for instance, if you are dealing with ideal gas, or let's say we are dealing with steam tables. So in steam tables, we have the exact value of entropy change. That would also include the entropy generation. But here we are calculating is as if there is no entropy generation. So the difference would then give us the entropy generation. That is what I think.
Okay, interesting. So, but these are internal irreversibilities, right? So one of the first concept we discussed today was if there is an reversible process, and we can find the entropy. So the change in entropy for that reversible process is equivalent to change in entropy for that irreversible process. So why do you guys think this specific entropy change will be different for these two processes? The states are same. Can you guys understand what I'm trying to say? So when we have
Okay,
same
so
states, when we
again, the
have same
question.
state, so when we have two states, and whatever be the process in between, whether the process is going through irreversible process or going through uh, reversible process, we said entropy is going to be a state function. So it's just it doesn't depend on path, right? So whether there is internal irreversibilities or without internal irreversibilities, provided the states are same, entropy should be changed, right? Same, right? Change in entropy. Picture, instead of reaching a state, let's say 1 to 2, if I have irreversibility, I will be reaching some other state 2 dash. Okay, at that time we will find entropy generation, and we will find the state, what is the second state, right? So here the state is fixed from 1 to 2. I'm going in one path, I have irreversibility, in another path I do not have irreversibility. So that is what the question is asking. Can you guys understand what I'm trying to say?
Okay, so there will be a if t dash if we are calculating like delta is generated. Uh, when we were calculating the delta is reversibility equal to generated plus reversible. In that case, we will be using any t dash equation. I mean, for the entropy compression, the adiabatic compression,
Right.
actual compression will be.
Right. So this is a if I plot it, if I plot it in, let's say, So let's say if I plot it in this graph, which graph? Let's say here we have P, and let's say we plot it in TS graph. Okay, and let's say we go from one temperature to second temperature. Right, temperature 1 is 400 to 600. It's not like this. This is 1 and this is 2. So there is one path which is reversible path. There is one more path which is irreversible path. So if the states are same, then change in entropy is going to be same. So I am telling delta S in and reversible path is equal to delta S in the irreversible path. Right? So now if you are instead of going to 2, you will be going to some other state 2S, right? That time your path, your 2S is different. You will have delta S generation. So given the states are same, you will not have any delta S generation. Or you know, we replace that irreversible path with any arbitrary reversible path. And since it's an irreversible path, we do not have delta S generation. Entropy change using that path. And since entropy change is it's a state function, we no need to worry about whether which path it is following. So be it without irreversibility or with irreversibility, you are going to get same entropy change. Is this clear? Anyone? Does anyone have any questions?
So if the we will be calculating the T dash if it is not given, it's reversible. It is reversible.
So state 1, and let's say you are asked to find state 2, right? And in the process there is a heat and there is some energy interactions. At that time, uh, you will if the process is reversible, you will not have any entropy generation. If the process is irreversible, you need to consider entropy generation and you need to find the state 2. So at that time you will be using that equation. Is that what you are asking, Francis?
Yes, sir.
Is that clear now?
Yes, sir.
Okay, if everyone is clear, shall we move on to next question?
Sir, one thing I want to say that,
Sure.
sir, if we are going in between the same states, 1 to 2, once we have traveled with the reversible path, other time we went with an irreversible path. So definitely the paths will be different. That is, whatever the work or heat transfer we are required to will be different for these for both of these processes.
Right.
But since we are dealing with the same states, the entropy change would be same. But then you said, sir, if we follow, let's say, the irreversible path completely, then we will reach at a different state. Let's say 2 dash. So, sir, in that particular case, the state is 2 dash, so entropy change would be different. So, there will be
Correct.
a different
Correct.
entropy. So, sir, then the difference of these two entropies will give us entropy generation, I guess.
Right. You if you know the state, let's say if you know the state 2 dash, right? And if you know
Yeah.
the state, then still now you can what you can do even if you travel in a irreversible path to 2 dash, you can replace it with a reversible path and again you can find the entropy change.
Yes, sir. Got it. Because we normally know the states.
Right, right. Normally, if we don't know the state, then we need to take of heat and work transfer in between, and we need to
Yeah.
find entropy generated. And using the entropy balance equation, we need to find the state.
Yes, sir.
That's
Now
where
I got it.
entropy generation comes.
Yeah. Thank you, sir.
So there is one more similar questions, but this time it's going to be calculation, more of calculation this time. Okay. Again, we have air, so it's an ideal gas. Remember, this is an ideal gas, so there is a possibility that you will encounter liquids. That there you can't use ideal gas uh, assumption. In fact, we also added one more assumption here. Here we used ideal gas. That's why we were able to get R, and we were able to we we were able to get this R here, and R ln of P2 by P1 we were able to get here because of using ideal gas assumption. If not, we will be having V by T, and PV is equal to nRT, right? So that part will come here. Okay. So there is one more assumption which I wrote already here. It's an ideal gas assumption. If you encounter liquids, you may need to change your maybe you need to use tables, and you need to find the entropies. Okay.
So just to confirm, thing, if we know the state, then we don't. Then the delta is generated and delta is reversible and the reversibility is same. And if we don't know the state, then if we find out the state to through reversible path, then in order to find the state for the reversible, we need to consider the delta is generated.
What we do is let's complete this. I have few more questions, right? So we will be dealing with entropy generation. So once we finish this, again I will address this question. Is that okay, Francis?
Yes, sir.
So whatever you said is right, but I want you to uh, uh, get the proper concept. That's what. Okay.
Okay, sir.
So here again we have air in a piston cylinder assembly undergoes a thermodynamic cycle. So it undergoes a thermodynamic cycle consisting of three internally reversible process. So it's a reversible process. You don't need to worry about anything in series. Okay. So we have a constant volume process and a constant pressure process and an isothermal heating process. Okay. Employing the ideal gas model with CP, which is also given, evaluate the change in entropy for each process. We need to find the change in entropy for each process. Sketch the cycle on PV and TS coordinates. Uh, Process associate work and heat transfer with areas on these diagrams respectively. This you guys can quickly tell me how to do it. So the important thing is we have ideal gas equation. We have Cp to be 1 kilojoules per kg Kelvin. So maybe let's try to first draw the diagrams so that you will be more clear. Let's draw PV diagram. PV. One is zero point 0.1 megapascal, 2 is 0.42 megapascal. Say this, and we have temperature. Find 1 to 2 is constant volume, so we will have a vertical line, right? This is going to be 2. We have constant pressure cooling. So when we cool, what happens? Will it be going this way or this way?
Temperature reduces and volume reduces.
Can you repeat, Francis? Sorry.
When temperature reduces, the volume will be reduced.
It's a cooling process, temperature reduces. All right. So volume reducing, we will be going, and it's a constant pressure. So it's going to be a straight line. isothermal heating to the initial state, so no problem. It's going to be. And since it's an isothermal, I directly joined. I should have asked you before. Uh, it is going to be straight line because it's an isothermal process, and we have PV is equal to nRT, right? And if isothermal means temperature is constant, so PV is a constant. Then it will be a straight line. Okay. I hope that's clear to everyone. So this is the PV, and else we need to know. We need to find the entropy for each and every process. Let's find for process one P equal to constant. This is P equal to this T equal to constant. So process 1 to 3 is constant volume process, and find it. Change in entropy from.
That will be CVL and P2
So the
CVL.
same equation what we did last time, right?
Yes, sir.
Gp
P2
then
yes, sir.
T2 by T1 plus R times comma P2 by P1, right? So okay. Now for that we need to find T2. Do we have T2? We don't have T2, right? So how do we find T2?
Percent temperature directly proportional, then we can.
So Hamid is telling CV ln of P2 by P1. Yeah, we can do that also. Can we do? With should it be CV ln of T2 by T1?
Sir, I use a relation which was in between Cp and Cv. I mean, delta S is equal to Cp ln of V2 by V1 plus Cv ln of P2 by P1. So there the volume is constant, so the
Oh, okay,
Cp
okay.
part will go to zero and we will be left with Cv ln of P2 by P1. So, yes, sir, there is one more relation we can use that will be Cv ln of T2 by T1. That will also give us the same thing because that is between V and T, so the volume part will be zero.
So it should be like yeah, R ln of V2 by V. I think it's plus V2 by V1.
Yes,
So
sir, plus.
if V2 and V1 is gone, then you can simply use this, right?
Cv ln of T2 by T1. Yes, sir, that will also work.
So yeah, so either you can use this, so this part will go to 0, where this is delta S 1 to 2, or you can use this. Both are fine. Anyway, we need to find T2, so that is there.
Yes, sir.
How do we
Yeah.
do? So the hint is we need to use equation of state. So that is the only way, right? So we have P1 V1 is equal to nRT1, and P2 V2 is equal to nRT2. Since volume is constant, uh, these two. So since volume is constant, P1 by P2 is equal to T1 by T2, right? You can get T2 to be T1 times P2 by P1. Is that clear, everyone?
Yes, sir.
So how do we get, so what is that? Can you guys quickly calculate? This P2 0.42 by 0.1. Getting T2 to be 1209.6 Kelvin. I hope everyone is getting the same. So, as Amit said, we can either use this or use this. Looks like this second formula is easy. Maybe we will use that. Okay. So to find CV, CV is nothing but CP minus R, and CP minus R is going to be 1000 minus 287, which is going to be 713 joules per kg Kelvin. Let's say if we substitute that, what is the delta is 1 to 2, 713 ln of T2 by T1. We just found T2 by T1, 288. So 120. So what is the delta S here? Okay, 1023.22. Wonderful. So it's going to be joules per kg Kelvin. So this is the process one. Okay. Now let's go to process two. Process two to three. Process two to three is pressure constant. Okay. P is equal to constant. Now from 2 to 3, what would be the value we'll be taking? Pressure is constant, so we can use the first equation, right? Cp ln of T2 by T1. And here it will be 3 T3. T3 by, this is going to be 0 because pressure doesn't change. T3 is in the similar way. Are you guys following? I don't know. Everyone becomes so silent.
For deltas 2 to 3, it will be for 1435.08. 2 to 3.
How much is it?
Uh, no, sir, I have used the T1 and T2. It's wrong.
It's a So we need to find T3, no? How do we find T3? See, drawn TS diagram also, and then it would be more simpler. See, if you look at it, from 3 to 1, it's an isothermal heating, right? So temperature doesn't change from 3 to 1. So which means T1 will be equal to T3, right? Actually, we no need to go forward, find V2, V1, and then try to find T3. Okay? Nothing but T3 is going to be T1. So maybe if you put that here, T1 by T2. So how much is this coming? I think Francis, you already did it. Maybe you need to add one minus to it.
So what I get is 1435.084. But I use the T2 by T1.
So it will be minus now. Okay, check. Yeah. So T2 by T1, so it's an inverse, right? You can write it like T2 by T1 inverse, and inverse can come in front. So it will become minus. Okay, change to be this, and here it's going to be this. Let's try to find process 3 to. I hope everyone is following. If you don't understand, please stop me. There's no problem. Process T to 1 is temperature constant. Now temperature is constant, so which from 3 to 1
CPLN V2 by V1.
by V1.
No V2, no V2, V3 by V1. No, V1 by V1 by V2. V1 by V3.
3, lot of things.
Yes.
So I know only these two equations. Is there any more equations? I think there's going to be a third equation, right?
Yes, so there is the involving CP, B and P.
So P3 is known, P1 is known, P1, P3 is known. So maybe an equation containing P1 and P3 would be helpful here. P1 and P3, right? So P we know in all states. So P here is going to be 1.42. Sorry, zero point 0.1 megapascal. Here it's going to be 0.42 megapascal. So equation containing P3 and P1 would be more helpful here. Yeah, maybe we if we use the same equation in this zero, we would be able to answer calculations maybe. So it might be P1 by T3 minus R ln of P1 by P3, right? This part is 0 because temperature is constant, so this can be written as minus R ln of P1 by P3. So let's say if we continue this, minus 287 ln of P1 is zero point 0.1, P3 is 0.42 megapascal. Since both are megapascal, I am not adding 10 power 6 here. So how much is this entropy? entropy change. Minus 411.7. I think there should be plus, Samir, because we have another. This is definitely going to be negative, and negative times positive, isn't it? Point. Oh, okay. Kilojoules per kg Kelvin. So now we have three entropy. As per the question, it's done. Only thing we need to plot Ts coordinate. But before that, let's try to find out what is delta S cycle, because it's in cycle, right? Let's try to find out that delta S of 1 to 2 plus delta S of 2 to 3 plus delta S of 3 to 1. 023.22 minus 1432 plus 411.87, which is the cycle, delta S cycle. 0.01. Actually, it should be 0. It's an let's have a look here. Process in series, because it's in cycle, or any cycle usually will have, provided the states are same, you are going to have 0 and change in a cycle. Okay, let's plot the TS diagram quickly. What is the process 1 to 2? 1 to 2 is 1 is temperature constant. Let's try to do that. Temperature constant at 288 Kelvin. Okay, so this is, let's say, 288 Kelvin. The other temperature is around 1209. Is it 129.6 Kelvin? So there's going to be 3 to 1. This is going to be 1. This is going to be 3. And it is also heating. So heating actually increases the entropy. This is a volume constant. So volume is constant and then pressure is constant. So maybe I can just randomly draw straight line or curved line. I will leave it up to you whether it's a straight line or curved line. But it will be something like this. So uh, to increase is an heating process, constant volume heating process. So heating will always increase the entropy. So it has to go this way. Entropy should increase. So it has to go this way. And this process is volume constant. And constant pressure cooling will decrease the entropy. So it has to come this way. All right. So this is how TS diagram looks. Uh, I think there is no question still now. Let's go to the third question.
So,
Yeah, Francis.
we have calculated all the state using the ideal gas equation, isn't it? So, for the even though the process is irreversible or reversible, we can find the state points using ideal gas.
Yeah, we can find.
So, but if the process is any adiabatic or anything, can we use the PV raised to gamma equation for calculating both the reversible and irreversible? I mean, we will be having that T1 by T2 equal to P1 by P2 gamma
So
minus
if
gamma.
it's an adiabatic, P, V, T, everything will change, right? So you cannot use only the equation of state to find the state variable. So you have to use PV power gamma equal to constant. You are right, true.
So in that case, can it be the same for the reversible and the reversible if we use that adiabatic equation P raised to gamma and also P1 by P2,
Which will be same? Which will be same? You're telling.
it will be same. Okay.
Like I'm asking which state variable will be same? You're asking for. Like you are telling same or
Yes, the entropy. Entropy and other state. I mean, we need to calculate that T1 and T2 dash. There was a case before.
so if you use this equation, ideal gas equation of state and the process like PV power gamma equal to constant, and if you are able to get the state variables, right? Then you worry about it. You can use the entropy formulas we have here.
So when we use that equation, we don't need to worry about the reversibility or reversibility when we find
Right.
out the
So the
state.
process will take care, right? So the process, if it's an adiabatic process, PV power gamma equal to constant. So your system is going to behave like that. If it's an polytropic process, PV power n is equal to constant. So that will be taken care within the system. Only when you can't find all the variables, equations, entropy balance equations. If you don't know, uh, it doesn't matter whether it's a reversible or irreversible. If the process index is given, the polytropic index is given, you don't need to worry about it.
Okay, sir.
Okay, so another question. An inverter claims that electricity generating unit shown in the figure receives heat transfer at a rate of 270 kilojoules per second at a temperature 298 Kelvin, and the second heat transfer at a rate of 380 and 400 Kelvin, and the third the rate of 530 kilojoules per second and uh, 560 Kelvin and at 560 Kelvin for an operation at steady state. Evaluate this claim. What do you think? By so he is telling that he will generate electricity by receiving heat from three reservoirs at three different temperatures. Do you think it's possible? I mean, without going into the question, we can simply say whether it's possible or not. Does anyone have any thoughts?
Sir, there is no electricity, I mean heat to electricity conversion present here or shown. So,
See,
uh,
okay, so
so normally we think about heat getting converted into mechanical energy, then it gets converted into electricity.
right.
So it's showing directly. So
So
maybe,
there is
sir,
some system. We don't know what is that system. Here we have inside some system,
yeah.
but thermodynamically, is it possible? It's my question. So it can be converted into mechanical, then it can be converted into electricity. It, it can be, they can even use Seebeck effect or something, and they can directly
Yes,
convert
sir.
into electricity. That is also possible. So we are not
Sir,
concerned about the system, but just by looking at it, can we say whether it's possible or not.
Sir, we can look at Clausius theorem, which says that q by del q by t has to be smaller than equal to zero. So if it is smaller than equal to zero, then it is possible. Otherwise,
Okay.
yeah. If
Okay, then
it's equal to zero, then yeah.
try to find out. Maybe we can use so whatever you said, but in a different way. We can use a entropy balance equation for a closed system, right? Uh,
Okay, sir.
yeah, the same thing. Clausius inequality is where we use that. So Clausius inequality system we can use, right? It's going to be ds is equal to uh, it's actually an integral. Maybe we can replace it with the summation of q j by tj plus sigma dot, right? This is where this sigma dot is the entropy generation. This is where we have this. J is wherever whichever boundary we are getting the heat, right? So here we are writing in terms of per unit time. So there is a second missing here. So everything is in per unit time. So maybe we can write this. This is also per unit time. Okay. So this can be summation of q dots by t. Sigma dot is also entropy generation. Okay, and since it's a steady state, this should be zero. So only this is going to be there. This can be written as q dot 1 by t. Reservoirs, we have three reservoirs, q2 by t2 plus q3 by t3. Sigma dot is equal to 0. So the Clausius statement checks whether this entropy generation is positive or not, right? So maybe if we rearrange this,
So ds by dt, how did it become zero?
it's a steady operation. Sure.
Okay, sir.
Operation is in steady state, so the change with respect to time is zero. So here we wrote in terms of total derivative. We easily convert this in terms of time derivative. Okay. So let's say if we do this, q1 dot is 270 kilojoules per second divided by t1, which is 280 Kelvin, plus q2 dot is 380 kilojoules per second divided by t2, 400 Kelvin, plus q3 dot is 530, okay, and divided by t3 is 560. All actually should be positive because everything is entering the system. So how much is it giving? So since everything is positive, it is actually straightforward that this is less than 0 and entropy generation cannot be less than 0. So even if we look at this simply based on statement also, it has to it is receiving heat from all the reservoir, but it is not rejecting heat to a lower temperature reservoir, right? So maybe if we collect all these three q dots and all the three reservoirs, and we can equivalently replace with one temperature and q reservoir, and you will see that it is taking heat and it is doing work, but it is not rejecting any heat. So like loosely speaking, using Kelvin Planck statement, it violates Kelvin Planck statement, so we can simply say the claim is not valid. But we can also prove it using this Clausius theorem, as Hamid said. So um, how much is this coming? For the sake of completeness, maybe we will look at it. 380 by 400 plus 530 by 560. All right, I am getting around minus 2 Page 6. Is that everyone getting? And this is less than 0, so the claim is invalid. Does that make sense to everyone?
So, for the place statement, it's actually cyclic integral of dq by dt equal to 0, isn't it?
For can you come again?
Actually, the closure statement is actually a cyclic integral of dq by dt equal to 0.
Right.
So,
It's less than or equal to 0, right? Isn't it? This I couldn't hear you.
okay, so in that case, how can we say that d is equal to q by t plus sigma generated? I mean, uh,
So this is a energy entropy balance equation, right, for a closed system.
okay,
So
sir.
do you? So we are dealing with closed systems here. Closed system which interacts with the surroundings only through energy interactions. So it is taking heat and releasing work. So we can even replace it like some hot reservoir and a cold reservoir, and we have some heat engine. Or here in this case, it's an electricity producing device where it is also work. Electricity is also kind of work, and it is taking heat. And instead of one reservoir, it takes heat from three reservoirs.
Okay.
Since it's an closed system, we can use entropy. Basically, that entropy balance equation is actually for closed system is derived from Clausius inequality. That's what Hamid is also trying to say.
So, for the Clausius inequality will be same for both reversible and irreversible. The Clausius inequality will be same for both reversible and irreversible.
Okay, so see, if it is equal to zero, the Clausius inequality is what is Clausius inequality? Cyclic integral of dq by t is less than zero, right? If it's in reversible, it will be equal to zero. Irreversibility will not be there if it's unreversible.
Yes, sir.
So that is actually so that's why we call it Clausius. For any process, you can replace it like this.
So, but since the entropy is a property, then the cyclic integral should be zero, isn't it? So, how can it be negative or greater than zero? I mean,
Can
dq by dt is like actually entropy. The entropy is a state variable. So the cyclic integral of any state variable should be zero state, irrespective of the reversibility or irreversibility.
why it should be cyclic interval of entropy? Is that what you're talking?
Cyclic integral of a state variable.
State variable.
Yes,
Which state variable you're talking about?
I mean any state variable cyclic integral should be zero state since the initial state and the final state will be same. So the cyclic integral will be zero, isn't it?
Right, right.
So the dq by dt is actually entropy. Then if we do cyclic integral of the entropy should be zero, isn't it?
Hmm. See, cyclic. Okay, I see what you're trying to say.
So, and also I have doubt that for in a cyclic integral for irreversible process, the dq/dt should be negative. So, is the entropy greater than zero for a reversible process comes when that negative sign inequality changes?
So that was one question at a time. I am still understanding your first question. So you are telling, let's say I have something like this. Okay, let's say I have 1, 2, 2. Say I go through a irreversible process. Okay, this is cyclic, right?
Yes, sir.
Okay, so now you are telling in cyclic integral of ds is 0, whether it's irreversible or reversible. Is that what you are telling?
Yes, sir.
So let's analyze it differently. So for any process, this is Cauchy's inequality is satisfied. Okay. So if the cyclic integral of dq by t is less than or equal to 0, then what it means is integral of dq by t using a forward reversible process from 1 to 2 plus integral of 2 to 1 using a reversible process dq by t is equal to 0, right?
Yes, sir.
So um, this part you can replace it only with uh, the reversible process. It's not equal to 0, it's less than or equal to 0, right? So that is what the statement says. Now ds is path is 2. I think I'm missing something. One second. Does anyone have any comments to add? Okay, let's try to find the cyclic integral of ds. Okay, cyclic integral of ds is ds at reversible path 1 to 2, sorry, irreversible path plus integral of reversible path 1 to 2, right? This is this, and you can replace the reversible paths cyclic integral. Anyway, ds is a state variable, that is fine. This you can replace with dq by t. Sorry, it should be 2 to 1. All right. So now irreversible path. This for this also you are telling you can write the same thing. Is that what you are telling, Francis?
So can you say once again?
So see, entropy function is this is defined like this. Let me see. Let's try to do two different things. One is cyclic integral of ds. Okay, cyclic integral of ds for this. cyclic interval of ds for so this uh, I'm taking this as an example from 1 to 2 and 2 to 1. Okay, so let's say if I have a irreversible process, this is IR. Okay, irreversible process times ts plus integral of reversible process from 2 to 1 ds. Okay, and let's try to write the cyclic integral of dq by t. Okay, and this can be written as irreversible process 1 to 2 dq by t plus integral of reversible process 2 to 1 dq by t. Okay, this is fine.
Yes, sir.
Now Clausius inequality says this should be less than 0. Okay, now what we know about ds is nothing but dq reversible by t. So which means, sorry, this is fine. Let me look at notes maybe. Um,
Okay, sir.
one second. Basically, they are trying to do the same thing. So what they are doing is, so you we can write ds as dq reversible by t, which means you can write it like integral. Here the reversible is ds, which is you can write it like reversible 2 to 1 dqr by t, right? So if that is the case, you can substitute. Oh, okay. Yeah. Yes. Mhm. So this is actually equal to 0. Since this is equal to 0, this part is equal to dqr by t integral of reversibility of 1 to 2 ds is nothing but um, so yeah. So if you add these two, let's say integral of r to 1 ds, this is already 0 plus, okay, subtracting 2 from 1, so they are subtracting from, so they took this as 2, this as 1. So this is also true. Okay, this is also equal to 0. This is Clausius inequality. That is also true. If you subtract 2 from 1, since it's already 0, integral of I 1 to 2 dq by t plus integral of r to dq by t is 1 2 from, okay, they are subtracting this plus integral of r1 to ds plus integral of r1 to 2 ds should be less than or equal to 0. So, and we found out, so reversible 221 dq and reversible, I'm sorry, this is also 221, right? So these two are same, so you gets cancelled, and you will get irreversibility of 1 to 2 dq by t plus integral of irreversibility of 1 to 2 ds less than or equal to 0. So when you subtracted, they change the sign. Okay. So, let's not do. Let's try to. So Francis, now I think I understood. So this is true. Okay, this is true. Entropy for a cyclic process is 0. That is also true. And Clausius inequality states del q by t is less than. Now, what you do is you try to substitute these two together. What we are trying to do is we're trying to understand, for a process, how does the entropy changes, right? So if you do this, dq by t plus integral of reversibility of 1 dq by t less than or equal to integral of irreversibility of 1 to 2 ds plus integral of reversibility of 2 to 1 reversible 2 to 1 ds, right? Now if you try to rearrange this, integral of reversible 1 to ds plus integral of reversible 2 to 1 ds minus integral of reversible dq by t minus integral of reversible t will be great. Now if you see this, now let's remove this reversible, and these two will go away, right? And which will eventually lead you to integral of irreversibility of 1 to 2 ds is actually greater than integral of dq by t 1 to 2 for an irreversible process, right? This you can replace it by greater, maybe equal to sign will be greater if it is reverse, if it is an reversible, then this ds will be equal to dq by t. If it's an irreversible, then there will be additional entropy generation, and based on that, what we do is we find the entropy balance equation. Okay, give me a minute. Balance for a closed system. So to remove this inequality, what we do is we can write it like ts is equal to dq by t plus some entropy generation. Okay, and that is how you get this here. So whatever you said is right. You need to use these two together for an irreversible process. Is that clear, Francis? Or do you have any more questions?
No, sir.
So what was this your question? How come? How did you get that?
Actually, what I have is that what I asked is the integral dq by dt equal to less than or equal to zero. There is a less than sign for a reversible process. The integral dq by dt will be negative as per the Clausius inequality. Uh, but since the entropy is an state variable, whether it is reversible or reversible, its cross integral should be zero. So then why the Clausius inequality say that irreversibility for irreversible process the integral dq by dt is negative.
So integral dq by dt is different. This is for a cyclic process. It says which is less than or equal to zero. But for a state variable, it is zero. So that's what we did, right? We tried to. It is so. These two are different statements. So you are telling these two are equivalent statements. You are telling, right?
Yes, sir. Yes, sir.
So you are telling here there is equal to, here there is less than or equal to. These two are should be equal to zero. Is that what you are telling?
Yes, sir.
So that happens only when you have reversible process everywhere, right? In the cycle, you will not have reversible process.
Yes, in cycle we will be having a reversible process.
Irreversible process too. So when you have irreversible process, dq by dt is not equal to just ds.
Uh,
So ds is equal to dq by dt, but dq by dt will not be equal to see. Okay. Um, would you like to add? What are you trying to say?
Sir, I wanted to say that for a process, entropy change depends entirely upon the heat transfer. If it is internally reversible, so it can be positive, negative, or zero. But when we are talking about a cycle from Clausius inequality, it has to be smaller than or equal to zero. And then if it's I mean to say reversible process, we use the equality sign. If it is irreversible, then we have to use the smaller than. And that balance comes because some energy gets destroyed and it takes the form of entropy generation. That is how the entropy change will still be there. I mean to say it will be similar because some energy is getting destroyed as entropy generation. So, looking at in a way that quantitatively there is a balance, but qualitatively there isn't
Yeah.
because energy, yeah.
So the question was, what he is trying to say is dq by dt.
Yeah. Yes, sir.
So if cyclic integral of ds is equal to 0, then why not in cyclic integral of dq by t is equal to 0?
Cyclic integral of dq by t, sir, I think it would be zero for a cyclic process. For an internally, for a reversible, internally reversible cyclic process, it will be equal to zero. If there will be some irreversibilities, we need to add the entropy generation part.
So the question was, uh, so we know that ds is equal to dq by t, right?
Yes, sir. Yes.
dq
Yeah.
reversible by t.
Yeah. Yes, sir. It is.
We can take any irreversible path and you can find dq by t, right? Now,
Yeah.
if you so if you replace that ds to dq reversible by t, then cyclic integral of dq reversible by t is equal to 0.
Yeah.
So Francis, it's if you think about it carefully. So yeah, I understood your question now, and I understood the confusion also. See, ds is dq reversible by t. Is that clear?
yes, sir.
Now cyclic integral of ds is 0. Okay.
Yeah.
So now you
Yes,
can replace ds to dq reversible, and you can crudely say that this is equal to 0, which means this is valid only for reversible process. because you found ds using reversible process.
Okay, sir.
Now if you have irreversible process, this is not valid because dqr is not an irreversible process heat, right? So you will have another entropy generation where it is not an irreversible process, but the Clausius inequality says it is less than or equal to 0.
Okay, sir. So, can we write actually the ds equal to dq reversible by t plus entropy generation?
This, uh, see, that is an entropy balance equation. It is not dq reversible, it's dq by t plus entropy generation. So it is not if there is a dq reversible, then it is not, then there won't be any entropy generation. You can write ds is equal to dq by t plus entropy generation. Okay? These two are equivalent. In a reversible process, there is no entropy generation. So what happens? Uh, Only the heat release divided by, but ds is same. See, these two ds's are same. It is reversible heat, but your process doesn't go through reversible heat. It goes to an irreversible process. So you will end up adding more heat. So more heat or less heat. So that has to be accounted to entropy generation.
Sir, I think we can put it this way. If we have, for instance, a system, let's say we have a constant volume, a simple, very simple system, and we are adding heat into it. So, let's say to get a state 2, we need to add certain amount of heat. If we are going with an internally reversible process, which is like to say very infinitely slow process, where we are actually keeping the temperature same, that amount of heat will be lowest to get that change of state. But if you are using a finite temperature difference, for instance, like normally we do, in that case, more amount of heat will be required to get the same state. In that case, some of the heat that we are adding is getting lost as entropy
Entropy
generation.
generation, true.
Yeah.
Yeah. Now is are you clear, Francis? Is that clear, or is do you have still doubt?
Okay, so actually, what he said is when during the reversal process, the q by t q reversible will be some. It will be used for entropy generation, some for heat projection.
Additional heat will be used for entropy generation. That's why we write in this form.
Okay, so dq by dt plus entropy generation is actually dq
Yes,
reversible by t. It will be a
exactly.
subset of dq reversible. Okay, sir.
It was a wonderful conversation. We'll try to finish this. Oh, we have fifth one. Okay. We'll try to finish at least fourth. Let's see. Okay. Um, so I hope everyone is on the same page. All right. So we have another. So I'm just having all the questions with air and ideal gas equations. Okay. So the air is at 600 kilopascals and 600 Kelvin, and a mass flow of this is enters the pipe passing through a overhead in a factory space. At a pipe exit, the pressure and temperatures are given. Okay. Air can be modeled as an ideal gas with K. K is actually gamma here. Kinetic and potential energy effects can be ignored. Determined at steady state the rate of heat transfer in kilowatt for control volume compress. Okay, let's break it up. Let's try to understand first half of the this thing. So we pipe. So air enters with temperature of 600 Kelvin and pressure of 600 kilopascal. Okay, and leaves at 550 Kelvin and pressure of 575 kilopascal. Okay, now air can be modeled as ideal gas. Okay, ideal gas with the gamma to be 1.39. kinetic and potential energies are ignored. Okay, determined at steady state one rate of heat transfer in kilowatt. Okay, so if you look at it, temperature is changing from 600 to 500 Kelvin, 550 Kelvin. So there is some heat loss from the pipe. Okay, heat is lost. Um, we are asked to find this heat. How much is this heat? And then rate of entropy production. Because of this, what is the rate of entropy production for an enlarged control volume that includes pipe and enough of its surroundings? So they are asking for an entropy generation for an enlarged control volume. It's not just the pipe but a surrounding too, which means crudely speaking they are asking for a entropy increase in a universe including system and the surroundings. Okay, that heat transfer occurs at ambient temperature of 400 Kelvin. So there is an ambient temperature T infinity to be 400 Kelvin. So uh, I don't know whether you all understood the question. So air is entering the pipe some certain temperature and pressure and is leaving the pipe at certain temperature and pressure. During this process, it exchange heat with the ambient. So we were asked to find what is the amount of heat and the entropy production in the during this process. Okay. So let's first try to find what is the amount of heat. We need to find Q. We have some mass flow rate also, m dot, which is 700 kg per hour. Your control volumes. Can we use it to find heat transfer rate? Does anyone have any clues? Steady flow energy equation. It is telling steady flow energy equation. So the questions in thermodynamics, heat transfer, and fluid mechanics, it will be very simple. The reason is we have only few conservation equations. One, we need to do mass balance, and then we need to do momentum balance in case of fluid mechanics. And now here, in case of thermodynamics and heat transfer, we need to do energy balance. Okay, and additionally, we will also do entropy balance when it's required. Okay, so there are only balance equations, and it is universal everywhere. One is mass, momentum, energy, and entropy balance if required. Okay, so here in this case we are dealing with energies. What is the amount of heat is getting out? So we need to use energy equation. So since it's in steady state, we can use steady flow energy equation. So what is the steady flow energy equation? So energy in equal to energy out. That's it. If I crudely want to write a steady flow energy equation, energy in is equal to energy out, right? Energy in is going to be m dot into h 1 plus kinetic energy plus potential energy, right? Plus if there is any heat input but some heat output, right? So we can write m dot into h2 plus some kinetic energy and potential energy. I'm not writing the full form of kinetic energy and potential energy because we are going to ignore it. Okay, so and then we have q dot. So if you look at it, we are just ignoring these things. You will end up getting a h1. This side is going to be m dot h2 plus q dot, right, into h1 minus h2 is equal to q dot, where h is cpt, right, m dot cp T1 minus T2 is equal to q dot. Basically, what is the temperature change is what you are getting here. And since the uh, there is no work, we are not adding work. That's it. So how much is it? The q dot? Q dot is leaving. So maybe what I should have done. Okay. Anyway, remember that q dot is leaving. M dot is 700 kilogram per hour. So it's going to be 700 by 60 minutes, 60 into 60 seconds. So it's going to be kg per second into cp. Okay, cp, we need to find cp also. Given is gamma is 1.39. So what is cp? Most of time I'm writing the formula for cp, gamma r divided by gamma minus 1. I hope everyone knows it. So you can use this cp, maybe 1.39 into r is going to be 287 divided by 0.39. Okay. And times T1, which is 600 minus 550. How much is the heat transfer? Nine 287 divided. So I'm getting 9.945 kilo. It's actually leaving, so please remember that. Which means you need to put a negative sign actually, q dot. So from the system it's leaving, right? Now we need to find entropy, entropy production. How do we find entropy production? Rate of entropy production. For that, we need to use the entropy balance equation, volume, right? Same thing. Entropy, how entropy can increase? Entropy can increase because of heat, because of mass entering and leaving, right? And due to production, because of irreversibilities present inside the system. These are the three ways entropy can vary. If you have work, you can add that also. So let's so entropy balance equation, like, and steady state entropy balance equation, which is going to be q in q. This is for s2 minus s1 is leaving, right? So s1 minus s2 entropy generation, sigma dot. And you are asked to find this entropy production, is it? You need to find entropy production. So you are asked to find this entropy production. Sigma dot is 2 minus s. Okay. Now you can substitute this here. So since q dot is leaving, please remember q dot is leaving, so minus of minus 9 point it's leaving to the surrounding with a temperature of 400 Kelvin, plus we have m dot, which is 700 by 3600, 700 by 3600 into S2 minus S1. Oh, how do we find S2 minus S1? Is this clear? Uh, think I rushed a little bit. So is this clear? First we did energy transfer. I mean, first we did energy balance to find the heat, because we need to use it for entropy balance, and we wrote a steady state entropy balance equation, and we are just rearranged it, uh, and we substituted the values for and all we know. Okay. Now we have S2 minus S1. So how do we find S2 minus S1? So this we already did, right? We have certain pressure and temperature, and it is going to a next state which is a certain pressure and temperature. So we know as formula, right? S2 minus S1 is nothing but delta S, which is Cp ln of, since it's an ideal gas, Cp ln of T2 by T1 minus R ln of T2 by P1. Since it's also an mass base, there is no number of moles coming here. There won't be coming into picture. If we substitute Cp, P again it's 1.39287 by 0.39 into ln of T2 is 600 by 550. Sorry, 550 by 600 minus R is going to be 287. Natural log of P2 is, what is P2? 575 divided by 600. So you can find delta S here, which is nothing but S2 minus S1. You can substitute it here. Okay. Substitute it in the equation, and you can find the entropy generation. Is that clear? Can you guys quickly find out what is the entropy generation? If you continue this, I quickly got in results. I don't know whether it is right or wrong, but please check it. I am getting something like this. So entropy generation, it should be positive. Entropy generation is 27.22 joules per kg Kelvin. Okay. So this is how you do for a control volume analysis. Like if it's an open system, this is how you do it. If it's a closed system, you have to do the, you have to use this method to do it. Okay. So there are two balance equations, one for closed and one for open. That's it. In principle, both are same actually. Is that clear for everyone? This question, everyone is silent.
Yes, sir.
Okay. Right. Thank you. Here we have another question. Let me quickly discuss. Maybe I will take 2 more minutes. So here we have a portion of ducting in a ventilation system operating at steady state. The ducts are well insulated and pressure is very nearly 1 bar through. Assuming the ideal gas model, again, ignoring kinetic and potential effects, determine temperature, exit diameter, and entropy production. So if you look at it, we have a duct system in a ventilation system. What we have is there is a fluid 1 coming and fluid 2 coming here. Both are almost, I mean, same fluid, which is air. So both are coming, mixing here, and coming out at 3. So we have a velocities, diameter, and temperature at 1 and 2. We are asked to find temperature and diameter of the duct at 3. Okay, and rate of entropy production during this. Okay, it's a well insulated, so there is no heat transfer. So this heat transfer is 0, and there is no work transfer also. That is also 0. So basically, what you have to do is, this is a combination of all the physics. So if you look at it, you need to find, you may need to use mass balance to find density density at the at the exit, right? You need to use energy balance to find the temperature, and you need to use entropy balance to find the entropy production. So I think it would be a good practice for you if you complete this, okay, by yourself. So basically, let me quantify it. So we need to find temperature. So we need to use. So first we have to use mass balance. We also have to use energy balance because we need to find temperature. Usually mass balance you can find velocity, but here velocity is given, instead diameter is asked for. So that's why you need to use these two for A and B. And for C you need to use entropy balance. Entropy balance, whatever we dealt before in the previous what do you say, question. Okay. So yeah, so you can do it on your own. If come to me, you can even post your questions in the common forum. Okay, I will be able to answer. Okay, let's conclude this session. If you have any doubts, you can stay back and ask. If not, let's meet next class. Thank you.